The mud at Ypres in 1916 didn't care about architectural theory. It swallowed tents, rotted timber, and turned every British encampment into a freezing swamp where soldiers died from exposure before they ever reached the trenches. Lieutenant Colonel Peter Norman Nissen watched this happen and did something revolutionary. He ignored everything architects knew about building and asked one question instead: what's the absolute minimum needed to keep men alive? His answer was a half-cylinder of corrugated metal. No foundation, no frame, no skilled labor, just curved steel sheets bolted together by exhausted infantrymen who'd never built anything in their lives. In March 1916, 6 soldiers erected the first Nissen hut in under 4 hours. By November 1918, over 100,000 of these structures housed British forces from Belgium to Mesopotamia. 25 years later, American engineers looked at Nissen's design and thought they could improve it. They added steel frameworks, insulation systems, electrical integration, and finished floors. They created the Quonset hut, a structure that was objectively more comfortable and technically more sophisticated than its British predecessor. They were also completely wrong about what warfare actually needed. The genius of doing less. When Nissen walked through supply depots in early 1916, he saw piles of corrugated iron sheets nobody knew how to use. These curved metal panels, originally meant for roofing, sat abandoned while men shivered in canvas tents that collapsed under snow. The Western Front had consumed all the timber. Skilled carpenters were in the trenches or dead. Traditional construction methods had become impossible. Every other engineer looked at this problem and tried to work within existing construction paradigms. They designed modified barracks that required less wood or reinforced tents that could better withstand weather. They were trying to make traditional architecture work with limited resources. Nissen took a different approach. He threw out traditional architecture entirely. His breakthrough wasn't adding complexity, it was removing it completely. He took those corrugated sheets and bent them into a half-cylinder. The curve meant the structure needed no internal supports. The metal itself was the frame, the walls, and the roof simultaneously. When you bolted one sheet to the next, you weren't just adding coverage. You were creating structural integrity. Each section overlapped the previous one by 3 inches, and the bolts went through 3 layers of metal, creating a continuous shell that distributed stress across the entire surface. This was architectural heresy. Every building principle since ancient Rome said you needed vertical framing, posts and beams cut and fitted with precision. Architecture was fundamentally about separating structural components from protective ones. The skeleton held up the building and the skin kept out the weather. Nissen eliminated the entire concept. His hut had no frame because the walls were the frame. The protective skin was the skeleton. Form and function collapsed into a single component. The construction sequence was brutally simple. First, lay wooden base plates in a rectangle. Second, bolt the first corrugated sheet to the base. Third, add the next sheet, overlapping and bolting it to the first. Repeat until complete. Finally, install wooden end walls. Done. A sergeant and 5 privates could build one in 72 hours. Completely inexperienced troops needed 4 to 5 days. The British Army tested this repeatedly at training camps in Dover and Southampton throughout summer 1916. The results were consistent. Anyone could build a Nissen hut with basic instructions and standard tools. When Nissen presented his design to British Army Command in April 1916, he made one promise that changed everything. Any infantryman could erect it in 3 days, and the materials could be transported on a single lorry. The War Office placed its first massive order in August 1916, 10,000 units before winter. By June 1916, Nissen huts were appearing across every British sector of the Western Front. During the Battle of the Somme in late 1916, construction units were erecting Nissen huts within artillery range, providing immediate shelter for wounded men being evacuated from the front lines. The American Assumption. In September 1940, Commander George Doria of the United States Navy toured British military installations to study their temporary construction methods. His classified report, filed in November 1940, devoted 18 pages to the Nissen hut. He documented assembly times, material specifications, and interviewed British construction officers who'd deployed them since 1916. His conclusion was direct. The Nissen hut was the fastest field structure ever designed, but American forces would need modifications. That single word, modifications, contained an assumption that would undermine everything that made the Nissen work. Doria assumed that because American industry was more advanced, American temporary structures should be more advanced as well. He never questioned whether more advanced meant more effective in combat conditions. American engineering culture in the 1940s simply didn't conceive that simpler could be superior. Complexity was progress. Improvement meant adding features, not removing them. This wasn't malicious or stupid. It was the natural product of American industrial success. The idea that the optimal military shelter might be a curved piece of corrugated metal with no frame was conceptually foreign. So when modifications began after Pearl Harbor, they started from a flawed premise that making the Nissen hut more like a proper building would make it more effective. When perfect becomes the enemy of good enough. The Navy Civil Engineering Corps chose Quonset Point Naval Air Station in Rhode Island as the development site. Commander John Barney Cyrus led the design team. The first American prototype emerged in February 1942, and it looked similar to the Nissen but carried fundamental differences. American engineers changed the structural logic completely. Where Nissen used corrugated sheets as self-supporting elements bolted directly together, the Quonset design introduced an internal steel framework. This framework consisted of curved steel arches that stood independently and supported the corrugated panels. The panels no longer carried structural loads. They were cladding attached to the frame with self-tapping screws rather than through bolts. Cyrus argued this approach would create stronger buildings capable of supporting heavier equipment loads and providing better anchor points for electrical and plumbing systems. He was correct on both counts, but he'd introduced complexity that Nissen had deliberately avoided. The framework requirement meant Quonset huts arrived at deployment sites as more components requiring more assembly steps. A standard 40-foot Quonset needed 14 steel arch ribs, each weighing approximately 90 pounds, positioned at specific intervals and bolted to foundation plates. Only after the frame was complete could crews attach the corrugated panels. Nissen assemblies started with the panels themselves and built outward. This philosophical difference added between 12 and 18 hours to construction time. Navy officials accepted the trade-off because they prioritized building permanence over deployment speed. But wars don't wait for comfortable assumptions. The steel framework created dependencies the Nissen never had. Each arch rib arrived as a pre-formed piece bent to precise radius. If one rib was damaged during shipping, the entire frame's geometry could fail. Nissen huts tolerated imperfection because the corrugated panels flexed and adjusted as crews bolted them together. The panels themselves corrected minor alignment errors. Quonset ribs had to align perfectly before any exterior panels went on. Construction crews spent hours using levels and plumb lines to ensure every rib stood at exactly 90 degrees to the foundation. On level concrete pads, this was manageable. In combat zones, it became a nightmare. The bolt count told the story. A 16-foot Nissen hut used approximately 200 bolts total. A 40-foot Quonset required over 700 bolts and screws. Every additional fastener was another opportunity for construction delays when tools broke or hardware went missing. The Pacific Reality Check. When the 804th Engineer Aviation Battalion arrived at Henderson Field on Guadalcanal in January 1943, they discovered that humid conditions had caused some steel ribs to rust at bolt holes during the Pacific crossing. The ribs couldn't be modified or replaced with local materials because the entire structure depended on those precisely formed arches. The engineers waited 3 weeks for replacement ribs to arrive from Pearl Harbor while troops slept in tents. Meanwhile, Australian forces supporting operations from Port Moresby used Nissen pattern huts manufactured in Sydney. When Australian ribs arrived with rust damage, construction teams simply cleaned the holes with wire brushes, added extra washers, and continued assembly. The self-supporting panel design meant perfect alignment wasn't critical. Close enough was good enough. Australian construction teams reported average assembly times of 36 hours. The Quonset also incorporated features absent from the Nissen design. Interior insulation became standard, sandwiched between steel panels and interior plywood lining. This meant 3-stage construction: erect the frame, attach exterior panels, then install insulation and interior walls. Nissen huts were single-stage construction. Once the corrugated panels were up, the structure was complete and habitable. Interior improvements came later, if time allowed. Electrical conduits were integrated into the Quonset framework during assembly. This created clean installations, but meant electricians had to work simultaneously with construction crews. In forward combat zones with limited personnel, this created scheduling conflicts. Wooden floors replaced the Nissen's packed earth. Quonset specifications required floor joists, subflooring, and finished flooring, all installed during initial construction. This added an entire phase of carpentry work before the hut was habitable. The speed that saves lives. At Camp Endicott in Davisville, Rhode Island, where CB battalions trained in 1943, instructors timed both systems. An experienced crew could complete a Nissen-style hut in 48 hours. The same crew needed 96 hours for a comparable Quonset with full insulation and interior finishing, double the time. When Admiral Chester Nimitz ordered development of Funafuti Atoll in the Ellis Islands during March 1943, Navy planners needed housing for 5,000 personnel within 60 days. The 2nd Naval Construction Battalion arrived with both Quonset materials and British Nissen huts, acquired through Commonwealth supply channels. Battalion Commander Lieutenant Commander Joseph Blunden split his crews to test both systems under identical Coral Atoll conditions. His official report in May 1943 provided exact figures. Nissen huts averaged 54 hours from first foundation timber to completed structure. Quonset huts averaged 91 hours, with the gap attributed primarily to framework alignment and interior finishing requirements. The speed differential became critical during emergency expansions. After the Battle of Midway in June 1942, the Navy needed immediate hospital capacity at Pearl Harbor for incoming wounded. Using Quonset huts would have meant a 2-week construction timeline. Instead, crews erected Nissen-style corrugated shells in 3 days, creating weatherproof spaces immediately. Interior medical equipment was installed afterward. Within 72 hours, those emergency wards had roofs, walls, and beds. Those wards remained in service through 1944, housing over 2,000 patients. When the ground won't cooperate. When Major General George Patton's Western Task Force landed near Casablanca on November 8, 1942, supply officers carried orders for immediate camp construction to support 35,000 troops using Quonset huts shipped from Virginia. Lieutenant Colonel Paul Thompson, commanding the 16th Engineer Battalion, watched his crews struggle with the steel framework in Moroccan coastal sand. foundation plates twisted when tightened because the sand compressed unevenly. This threw off rib alignment, which propagated geometric errors through the entire frame. Thompson's after-action report noted his crews needed 4 days per Quonset hut in Moroccan conditions, with most time lost stabilizing foundations and shimming framework ribs to compensate for uneven settling. British forces at the same North African theatre were simultaneously deploying Nissen huts shipped from Alexandria. The 512th Specialist Team Royal Engineers set up a field hospital outside Algiers starting November 12, 1942. Working with local Algerian labourers who spoke minimal English, the team completed 16 Nissen huts in 9 days. Their technique eliminated foundations entirely. They laid railway sleepers directly on graded sand, bolted the corrugated panels to those sleepers, and stabilized everything with sand berms piled against the exterior base. The curve of the Nissen design meant the structure became increasingly stable as more panels were added because the weight pressed downward and outward. When windstorms hit in late November, several Quonset huts under construction toppled because their frameworks weren't yet clad with panels. The frameworks were top-heavy, with all that structural steel concentrated in vertical ribs with nothing to brace them. The Nissen structures, already complete with their self-supporting shells, stayed standing. A Canadian unit at Vimy Ridge in March 1917 had erected a Nissen hut during active bombardment, working in 30-minute shifts between artillery barrages. The structure was operational within 18 hours, immediately housing 40 wounded men evacuated from the Ridge assault. Try that with a Quonset hut. You can't. The framework has to be perfect before it's stable enough to survive weather, let alone shelling. The flexibility that wins wars. What separated the Nissen from the Quonset was adaptability to circumstances that deviated from the plan. And in war, circumstances always deviate from the plan. Nissen designed around what could actually be produced under wartime conditions. The corrugated steel sheets were 26 gauge, thick enough to resist damage but thin enough that 3 men could carry a section. Every bolt was 7/16" diameter, the same size used in ship construction, meaning supply chains didn't need special inventory. The wooden components came from whatever timber was available. Nissen specifications allowed for pine, oak, or even salvaged wood from damaged buildings. Field adaptability made the system nearly universal. In Mesopotamia during 1917, British forces built Nissen huts without the wooden end walls, instead using bricks scavenged from ruined villages. In Egypt, engineering units set the bases directly on sand and used interior poles cut from local palm trees. The core principle remained. Those curved corrugated sheets would form a weatherproof shell, regardless of what you did with the rest. Quonset production emphasized standardization that paradoxically reduced field flexibility. Components were manufactured to tight tolerances in stateside factories. When a Quonset rib arrived damaged, you couldn't substitute a local equivalent. The curve radius was calculated to quarter-inch tolerance. You either had the right rib from the right factory or you had nothing. The rigid standardization created a supply chain dependency that Nissen huts avoided entirely. The cost of comfort. In 1943, a complete 40 by 20 Quonset hut cost the Navy approximately $850. A comparable Nissen hut cost approximately $230 in inflation-adjusted 1943 currency. The Quonset was 370% more expensive. The Quonset's superior comfort and electrical systems justified the higher price in American procurement doctrine, but that cost increase mattered significantly when multiplying across thousands of units. Total American expenditure on Quonset production exceeded $140 million by war's end. For that same money, using Nissen hut pricing, American forces could have deployed over 600,000 huts instead of 170,000 Quonsets. Production volume numbers told competing stories. The United States manufactured approximately 170,000 Quonset huts between 1941 and 1946, an average of 34,000 per year. Britain produced roughly 100,000 Nissen huts during World War I alone, between 1916 and 1918, averaging 50,000 per year, with far less industrial infrastructure. The difference wasn't manufacturing capability, it was design complexity. Nissen huts required corrugated steel sheets, basic fasteners, and rough timber. Any sheet metal facility could produce components. Quonset huts needed specialized steel forming for the arch ribs, precise die cutting, and coordination between multiple suppliers. What happens after the fighting? After initial construction, Quonset huts could be upgraded in ways Nissen huts couldn't match. Crews could add partition walls, install heating systems, and mount heavy equipment to the steel framework. These capabilities made them suitable for permanent installations. Naval Air Station Alameda in California received over 400 Quonset huts in 1943 that served as workshops, classrooms, and administrative offices. Many remained in service until the base closed in 1997, some for over 50 years. That longevity validated the American approach for installations where permanence mattered more than construction speed. But the framework that enabled those upgrades became a liability in temporary field use. When the 43rd Infantry Division moved from Guadalcanal to New Georgia in June 1943, they couldn't disassemble and transport their Quonset huts. The steel ribs, once bolted together, were difficult to separate without damaging threads. The entire camp infrastructure, 42 Quonset huts, stayed behind, abandoned. Nissen huts disassembled almost as quickly as they erected because the bolted panels separated cleanly and could be reused elsewhere. British forces routinely relocated Nissen camps, moving the same structures from Egypt to Italy to Greece as front lines shifted. This wasn't a minor operational detail. It was the difference between mobile and static warfare. The lesson nobody learned. The fundamental problem with the Quonset wasn't that it was bad architecture, it was that it answered the wrong question. American engineers asked how to make better shelter. Nissen asked how to make faster shelter. In peacetime, better matters. In war, faster saves lives. When the 1st Marine Division was fighting in Guadalcanal mud during late 1942, having a weatherproof structure in 3 days would have mattered more than having an insulated structure in 10 days. When field hospitals needed immediate expansion after major battles, speed of deployment determined how many wounded got beds versus dying in triage tents. On Guadalcanal, Gunnery Sergeant Robert Leckie described watching construction crews work in 100-degree heat. The steel framework components were too hot to handle by mid-morning. Crews worked abbreviated schedules, dawn until 10, then evening until dark. This stretched 5-day construction estimates into 2-week realities. The Quonset improved everything about the Nissen except the one thing that mattered most in combat, getting soldiers out of the mud and into shelter before the next bombardment started. Modern military doctrine has largely forgotten this calculation. Current U.S. military construction standards assume infrastructure will be in place before major troop deployments, that supply lines will be secure, and that construction can happen without enemy interference. The Marine Corps recognized this gap in 2019 when they reintroduced Expeditionary Advanced Base Operations, essentially relearning the lesson that speed of deployment matters more than comfort of facilities. The architecture of necessity. The 170,000 Quonset huts America produced represented genuine industrial achievement. They provided shelter for millions of personnel across every theater. They served well as semi-permanent base infrastructure, but they couldn't match what 6 British soldiers accomplished in 1916, building weatherproof shelter in 3 days with nothing but hand tools and determination. That capability, that speed, that brutal simplicity was the actual innovation. The Quonset improved everything about the Nissen except what mattered most. When World War II ended, the United States found itself with approximately 70,000 surplus Quonset huts. The War Assets Administration began selling them to civilians in 1946 for between $200 and $600. Over 15,000 Quonsets were purchased by farmers, small businesses, and housing desperate families. The integrated floors, insulation, and electrical systems made them immediately habitable. Drive through rural Iowa, Kansas, or Nebraska today, and you'll still see Quonset huts serving as machinery sheds. Small airports used them as hangars through the 1970s. The University of Illinois housed returning veterans in a Quonset village from 1946 until 1972. They succeeded in civilian use precisely because of the features that slowed their battlefield deployment. Britain took the opposite approach with Nissen huts after 1945. The military wanted them gone because they symbolized wartime austerity. Thousands were dismantled, with corrugated panels sold as scrap metal during the post-war steel shortage. The British government actively discouraged civilian retention because they wanted to distance national identity from wartime temporary architecture. But civilian success isn't military victory. The corrugated curved huts still scattered across former war zones are monuments to different philosophies. The surviving Quonsets prove American engineering made them durable enough to outlast their intended purpose. The vanished Nissen huts proved British engineering made them simple enough that armies could build them anywhere, anytime, under any conditions, and then abandon them without regret when the front lines moved forward. Both approaches worked, but only one could be built while the shells were still falling. Peter Nissen understood something the American engineers missed. In war, the perfect is the enemy of the good enough, and good enough, delivered in 72 hours, beats perfect delivered in a week, every single time.